Hello and welcome again in the lecture of VLSI technology. And our today's topic of discussion is epitaxy and epitaxial growth. Okay, epitaxy, a transliteration of two Greek words, epi meaning upon and taxis meaning ordered, is a term applied to processes used to grow a thin crystalline layer on a crystalline substrate. If you might remember the basic growth of CMOS, है ना? How the CMOS is actually manufactured. Then you might have heard about the dopants. You might have heard about the body, and then substrate is doped inside that, and then there will be a silicon layer over that, SiO2 layer for the insulation, and then we will prepare the gate, drain, and source terminals by providing the electrode connections and all those things. So epitaxy growth is the basic of that. How a thin crystalline layer on a crystalline substrate is grown is nothing but the epitaxy. In the epitaxial process, the substrate wafer acts as a seed. Okay, it acts as a seed crystal. Epitaxial processes are differential from the Joraskli process described in chapter 1 all the in that in that the crystal can be grown below the melting point. Okay, so what we discussed in previous lecture, that is the Joraskli process we discussed in the previous lecture, if you remember. So the crystal can be grown below the melting point in that process. Okay, most epitaxial processes used chemical vapor deposition technique, which we are going to study later. A different approach is molecular beam epitaxy, MBE, which uses an evaporation method. These processes will be described in section 2.2 and 2.3 respectively. So we will be seeing these particular things later in this chapter. When a material is grown epitaxially on a substrate of same material, such as silicon grown on silicon, the process is termed homoepitaxy. Remember this. If silicon is grown over silicon, same substrate is grown over the same material, then it is known as the homoepitaxy. If the layer and the substrate are of different materials, such as aluminium gallium arsenide or aluminium gallium material, the process is termed heteroepitaxy. Homo and hetero. So homo represents the same and hetero represents the difference. However, in heteroepitaxy, the crystal structures of the layer and the substrate should be similar if crystalline growth is to be obtained. Okay, so this is also important. Silicon epitaxy was developed to enhance the performance of discrete bipolar transistors. These transistors were fabricated in bulk wafers using its resistivity to determine the breakdown voltage of the collector. However, high breakdown voltage necessarily need high resistivity material. ठीक है? This requirement coupled with the thickness of the wafer results in excessive collector resistance that limits high frequency response and increased power dissipation. So what it is suggesting, if I am interested in the high resistivity of the breakdown voltage, if I am interested in high breakdown voltage, I need to increase the resistivity. But while increasing the resistivity, the consequence is that it will decrease the frequency response, it will limit the frequency response, and also it will increase the power dissipation. Obviously, if you are increasing the resistivity, power will be more dissipated. Okay. Epitaxial growth of a high resistivity layer on a low resistivity substrate solved this problem. So how scientists have solved this problem? By growing the high resistivity layer on a low resistivity substrate. Bipolar integrated circuits utilize epitaxial structures in much the same way discrete transistors. We will see the figure in the next page. So how the discrete transistors utilize them? The same way the bipolar integrated circuits utilize the epitaxial structures. Okay, the substrate and epitaxial layer have opposite doping types to provide isolation. And a heavily doped diffusion layer serves as a low resistance collector contact. Unipolar devices such as the junction field effect transistors JFET employ an epitaxial wafer, as does the VMOS technology. Okay, so let us go ahead and see further details related with this particular topic. And this is the figure which I am telling you. I was telling that we will see. Let us go to that figure. This is the cross section schematic of an epitaxial, the B pattern of an epitaxial wafer used for integrated circuit fabrication. Part A represents the rectangular pattern. A represents A present on the substrate prior to epitaxy, whose location is shifted by L and shape distorted to shape B by the epitaxial process. So A becomes B after the epitaxial process. Okay, this is the P substrate. P substrate is having the 500 micrometer and 10 micro per centimeter of 10 microcentimeter of the resistivity, and then you are doping the N types of diffusion material. Buried layer is there. This is the N epitaxial layer over the P substrate. So this is nothing but the heteroepitaxy. So epitaxial structures have also been used to improve the performance of dynamic random access memory (RAMs), DRAMs, and CMOS ICs. In JFETs and VMOS circuits, the doping profile provided by the epitaxial process is integral to the device structure. In the dynamic RAMs and CMOS circuits, device could be fabricated in bulk wafers, but certain circuit parameters are optimized using the epitaxial material. So this is nothing but the purely a theoretical description what it means. I mean, the epitaxy growth is mean. The functional advantage of epitaxial wafers over bulk wafers are thus twofold. The advantages of epitaxial wafers over bulk wafers are thus twofold. Why? Why it is twofold? Because in dynamic range and CMOS circuit, devices could be fabricated in bulk wafers, but certain circuit parameters are optimized using the epitaxial material. So if I am taking the epitaxial wafers, I need not to optimize those, because it is already optimized using the epitaxial material. But if I am taking the bulk wafer, then I have to go for the optimization using the epitaxial process. So this is how the things are there. So the explanation of twofold advantages are given here. First is the epitaxial layer on a substrate often containing one or more buried layers offer the device designer a means of controlling the doping profile in the device structure beyond that available with diffusion or ion implementation. So what is the first advantage? If I am taking the epitaxial layer, then I have full control, I have full authority to select that how much doping I need to perform, how much doping I need to do in order to manufacture my application of IC or my type of IC or whatever I desire from that particular IC. Okay, this is not possible in case of the diffusion or ion implementation. So epitaxial growth provides you that flexibility. For example, the physical properties of epitaxial layer differ from the bulk material. For example, epitaxial layers are generally oxygen and carbon free, a situation not obtained with the melt grown silicon discussed in chapter 1. So in the previous lecture, when we were discussing about the puller mechanism and the puller apparatus, there we discussed that the oxidation layer was formed, and that was the disadvantage. So we needed to remove that oxygen layer by using some high temperature techniques. But here in case of the epitaxial layer growth, the oxygen and carbon are not present. So our time and effort and the cost also saved. So this is how the epitaxial growth has been introduced in this particular chapter. And still in the unit 1. Now we are not moved to the unit 2. We are still in the unit 1, and we are learning the basics of IC manufacturing technique. Let me go ahead and discuss with you the vapor phase epitaxy. This section is concerned with several aspects of silicon vapor phase epitaxy, such as process chemistry, aspect of process hardware, and current capabilities. The CVD, which stands for chemical vapor deposition of the single crystal silicon, is usually performed in a reactor consisting in element form of a quartz uh, reaction chamber into which a susceptor is placed. The susceptor provides physical support for the substrate wafers. Deposition occurs at a high temperature where several chemical reactions take place when process gases flow into the chamber. So this is actually that picture which we are talking about. Okay, let me fix this first. Yeah. So this is the boundary layer formulation of the horizontal reactor. We will discuss about it. Let us first discuss some basics. Basic transport processes and reaction kinetics. A thorough study of deposition process involves examining the thermodynamics and kinetics of the chemical reactions and the fluid mechanics of the gas flows in the reactor. So it is important to learn about the basics of wafer deposition before going ahead. So let me give you the basic idea about that. Oh, just a minute. Yes, as a starting point of discussion, the fluid mechanics of the gas flow, let us consider the Reynolds number Re, a dimensionless parameter that characterizes the type of fluid flow in the reactor. So this is the Reynolds number, where Dr is the hydraulic diameter of the reaction tube, V is the gas velocity, rho is the gas density, and mu is the gas viscosity. Values of Dr and V are generally several centimeters and tens of centimeters per second, respectively, for industrial processes. These parameters results in gas flow in the laminar regime. Since Re is less than 2000, accordingly, a boundary layer of the reduced gas velocity will form above the susceptor and at the walls of the reaction chamber. The thickness of the boundary layer Y is defined as this. See, this whole subject is based on the physics of how the chemical reactions are going to be placed, going to be processed in form of the solid or in form of the gas. Okay, so you will be finding lots of these kind of equations in your syllabus, and it is totally physics and chemistry based process, because we are actually learning that how the IC is manufactured. So physics and chemistry is always there. You will find always the reactions, always the formula, always the chemical reactions, in terms of the chemistry or in terms of the physics. So be prepared for this. The carrier gas is usually hydrogen, and using its typical values of rho and mu in the equation 1 results in the Re of about 100. Okay, so figure 2 shows the boundary layer forms at the inlet to the reaction chamber and increases until the flow is fully established. Although fully established flows are not always encountered in the short lengths of typical reactors, it is across this boundary layer that reactants are transported to the surface. The reactions byproduct diffuse back across the boundary layer and are removed by the main gas stream. The fluxes and species going to and coming from the wafer surface are complex function. So that was the figure which was there. Let us see that figure. This is the flow. This is the susceptor. Lower boundary layer, upper boundary layer. This is the central core. C is the concentration profile. V is the velocity profile. T is the temperature profile. So depending upon our need, we will be modulating these things. Reactant concentration charges. This is the decreasing, this is the acceleration in the y direction, and as we are moving towards this, the reactant concentration charge decreases and velocity increases, temperature changes also increases. So velocity changes and temperature changes increases along the x-axis, whereas the temperature changes increases in both the axes, velocity changes increases only one in one axis, and the reactant concentration changes decreases across both the axes whenever the flow is maintained inside that chamber. Okay, so let's go ahead and see some other uh, fundamentals related with this particular process, and then we will finish today's lecture. Okay, so this is the convention of the flux that is defined as J equals to D into dn upon dy, where approximation is J equals to dng minus ns upon y, where ng and ns are the gas, stream, and surface reactant concentrations respectively. D is the gas phase diffusivity, which is a function of pressure and temperature. Y is the boundary layer thickness, and J is the reactant flux of molecular per unit per time. Okay, so I'm not going into the details of all these things. That is not required actually. So basically, what we'll learn today, we'll learn that how epitaxial growth happens, what are the advantages of epitaxial growth over the bulk wafer, and why epitaxy is important and needs to be considered when going for the IC manufacturing, and its advantages over the puller mechanism, the puller apparatus, which we discussed in the previous lecture. Okay, so in this lecture, we will talk about the some basic fundamentals, and then we will move ahead with the contents. And most probably, in the next lecture, we will be talking about the reaction kinetics. So today we discuss about the physical parameters, and next lecture we will discuss about the chemical parameters, which is related to this particular chambers. Okay, thank you for watching this lecture. We will